There are tabulations of character tables for all the point groups that are relevant for molecules. So this is something that you'll be able to look up in various sources along the way. You will almost never have to generate your own character table, and that's certainly true in this course. What I'd like to do is talk a little bit about the information that's contained in a character table and relate it to some of the things that we've talked about already. Now, what I've drawn up here is a C3V point group character table of the type that we have derived in a different video. And you'll notice that each of the 6 symmetry operations is listed across here, and the 3 irreducible representations are listed as a column here. This is a typical representation of a character table where we list the representations in various rows. Each row is a different irreducible representation, and the symmetry operations each has its own column within that. All right, now we've noted that in fact these 2 operations belong to the same class. And the class in this sense is defined as operations that are related to one another. These use the same C3 axis, so they are related to one another in that sense. These 3 sigma v planes are related to one another because they all contain the z-axis, which is the principal axis of rotation here. And each of them, in effect, does a similar or a comparable operation on the object or on the molecule. Now, one of the things that you should observe is true for this is that as we look at this table here, all of the elements in each of these columns that belong to the same class are in fact identical. Same is true for these 3 columns. In other words, we have same information given for a class. Now, for this reason, we tend to go toward a simpler representation of the character table, which is shown over here, where instead of showing each of the individual symmetry operations, we group them together in the various classes. So this is a way of simplifying the character table. Now, we've mentioned already that the number of classes equals the number of irreducible representations. So when we do this, this means that the character table itself will be square. There will be as many rows listed here for irreducible representations as there are symmetry operations for the different classes. This also allows us to avoid the repetition that's involved when we include more than one column that belongs to the same class, because those will just be identical. All right, now you'll notice that we have indicated some labels now for these irreducible representations that we didn't see before. And I want to talk just a little bit about what those labels mean. They basically convey something, a couple of things. They convey something about the dimensionality of the irreducible representation. So for example, if the dimensionality is 1, then the label will be A or B for that. And what's the difference between A and B? A is symmetric with respect to transformations that involve the principal axis, and I'll just label that as Cn. So symmetric with respect to Cn rotations. And you can see that that in fact is true here. This is the principal axis, C3. These are both 1. So these tell us automatically that these 2 representations up here are going to be A-type rotations. We typically give the first one the subscript 1, the second one subscript 2. The A1 is one that we generally will associate with the totally symmetric irreducible representation. And it's usually the very first one listed in a character table. So you should expect to see all 1s across the row, the first row of the character table. B are ones that are not symmetric or anti-symmetric with respect to this C rotation. What does that mean? That means for the first element, the first one will be A. For all of the B's, we would have a -1 in this position. So there would be -1s there for B-type irreducible representations. All right, what about if D equals 2? Well, we already can see what happens there. We end up with a new label, E. And this is the only label you'll ever see for a 2-dimensional irreducible representation. All right, so when you see a 2 here, you should expect to see an E there. Those two go hand in hand. All right, and there aren't separate subtypes, although you can have more than one E-labeled irreducible representation in a point group. Now, for D equals 3, you will see the label T. This is, I'll say, relatively rare. You will find this mostly in descriptions of the cubic groups, that is, the ones that have tetrahedral symmetry or octahedral symmetry or icosahedral symmetry, something like that. Those are the places where you will find irreducible representations that have dimensionality of 3. Now, I want to talk about some general features here, some of which we have already discussed, but it's always good to summarize them when we have a chance. General features. Okay, 1, number of irreducible representations equals the number of classes. Okay, so these are all square tables. Okay, second, we know that the dimensions of this representation can be 1, 2, 3, and so forth, and each of these has different labels. For 1, it's A or B, for 2, it's E, for 3, it's T, and I don't know if there are labels for higher dimensions. I don't think there are, because in 3 dimensions this is probably the best you can do. All right, so we're going to typically label the character that appears for these things as chi sub I. I represents the irreducible representation, and R represents the symmetry operation. So I is the irreducible representation, and R is the symmetry operation. All right, so this is just a notation that we'll typically use, but these represent the various entries in this table. So chi sub I refers to which row it's in, R refers to which column it's in, and this is the character that's actually listed in that position. Okay, and I should have mentioned under the dimensionality that we, of course, still have this relationship between the overall order of the group and the sums of the squares of the dimensions of the irreducible representations. All right, and finally, as we've noted here, all the characters in operations of the same class are identical. All right, in other words, we will get similar columns here when we're talking about, for example, 2 operations that belong to the same class. Okay, so let's take a look at a couple of examples other than ones that we've actually physically worked on and see if we can see some of these patterns. So here are 2 different character tables, one for the C2H symmetry group and one for the D2D symmetry group. All right, now one of the differences I'll notice that we haven't talked about before is I don't have 1s and 2s as subscripts here. I've got G and U. Those should look familiar to you because they are related to inversion symmetry. So you will only see these labels in a character table when you have a group that has the inversion operator, as C2H does. Now you'll note that when it's G, we get 1s. When it's U, we get negative 1s. All right, G is symmetric with respect to inversion. U is anti-symmetric. That's why we end up with those numbers. Now you'll also notice that I have 1s here. The A labeled irreducible representations are symmetric with respect to the axis, the rotation about the principal axis. The B's are not. Okay, so here you can clearly see the separation between A's and B's. The top one here is the totally symmetric representation, all 1s, and that will generally be true in any character table for a point group. Now, I've also shown over here, and I didn't mention this on the earlier slide, but over here we have listed the various vectors or rotations that can be used to form a basis for those irreducible representations. So for example, if I were to look at the symmetry operations on a vector along the z-axis, with z always representing the principal axis of rotation, this would be those sets of irreducible representations that correspond to the operations of this symmetry group on a vector along the z-axis. Now you'll notice that both x and y give rise to the same irreducible representation. Since I don't have a parenthesis around x and y, these are each individually able to generate this irreducible representation, and they are not connected to one another as they were in the C3V case. All right, and we have the three rotations. RZ gives us this totally symmetric one. RX and RY separately give us the BG irreducible representation. All right, notice that from this we can also see I don't have identical columns here, so each column is an individual class, so I have 4 classes. These result in 4 irreducible representations, and the order of my point group is 4, and that's just equal to 1 plus 1 plus 1 plus 1, the sums of the squares of the dimensions of the irreducible representations. All right, so all of these things are things that we can now begin to look at this table and I hope appreciate some of its fine character. All right, what about this D2D point group? And I won't spend as long talking about this, but I'll just point out a couple of things. One, we have a couple of classes that involve more than one operator. All right, each of these involves 2 operators, so these are each individual classes. So I have a total of 1, 2, 3, 4, 5 classes and a total of 5 irreducible representations. Notice that 4 of these are A's and B's, so I know that they're all one-dimensional representations. There's one representation that is 2. This is a 2-dimensional representation, and it has the label E. All right, the A's are symmetric with respect to the principal axis. In this case, the principal axis is not a proper rotation, but an improper rotation. All right, and that is reflected by 1s in this column for the A irreducible representations and -1s for the B's. Okay, the other labels don't have the same kind of direct meaning for that. Again, we can see the various vectors that and rotations that generate these different irreducible representations. Z generates the B2 irreducible representation. RZ generates this one. And X and Y are the ones that are inextricably linked in the 2-dimensional irreducible representation down here. All right, so I hope this gives you a sense that when you look at a character table and look in collections of character tables, you can begin to extract some meaning just by looking at the table. It will tell you something about these different types of symmetry operations. Now, I want to close with one further little observation that I hope will be helpful. And that is, you may wonder, here I've got a point group that has only one-dimensional irreducible representations, and here I have a point group that has a 2-dimensional one. Is there a way I can predict what the dimensionality I might find in the group? And there is, and let me give you a little bit of that clue. If I have no axes of rotation, it will always have dimensionality 1. It will have an order of 1 or 2, and all of these will have dimensionality of 1. Okay? So in fact, they'll all be labeled A in this case. If I have only C2 axes, okay, remember C2 is a rotation through pi. So that means I can align the C2 axes and any reflection planes along the Cartesian coordinate system. So again, we will have all of our dimensionalities will be 1, and so all of our labels for the irreducible representations will be A or B. If I have one Cn axis, that is a higher order axis, so this is for n greater than 2, then I'll have dimensionality of my irreducible representations of both 1 and 2, so I will see A, B, and E type irreducible representation. So that's what we're seeing here. I can also have multiple higher order axes. That is to say, multiple order 3 axes or order 4. All right, and when I have this, then I can have dimensionality of my irreducible representations of 1, 2, or 3. So I will have labels for them of A, B, E, and T. And these are the ones that we typically find in the cubic groups, things like tetrahedra. All right, so in effect, if you simply look at what is the highest order rotation axis in the symmetry group, then you can immediately tell what the dimensionality of its irreducible representations is likely to be. All right, for these first two, it can only be 1. If it has a CN axis with n is greater than 2, it must have at least one irreducible representation of labeled E. And if it's got multiple axes that are greater than 2, then it will have almost certainly a irreducible representation with the label T and dimensionality 3.